Have you clicked off the video yet? Hello everybody, my name is Bear from Bear Science Lab, and before we start this lecture, I'd like to remind you about Black History Month. So let's celebrate Black History Month and the role of black scientists in our community by going to this website right here, blackscientist.tech. And now, let's start the day off with some magic. So I'm gonna throw these two guys, and I'm gonna catch them while my eyes are closed. 3, 2, 1. Oh, damn, the magic didn't work this time. Guess I'll just have to reproduce 2 more markers. 3, 2, 1. Aha, you see? That's the power of magic. All right, I'm going to tell you that Newton's first law is constant momentum. Newton's second law is change in momentum. And Newton's third law is conservation of momentum. All right, so let's start with Newton's first law. So Newton's first law basically says that if an object is at rest, so if an object is at rest, it will stay at rest until there is an unbalanced force. Or in other words, sigma F is equal to 0 or not equal to 0. So, for example, in this case, when a box is just sitting on the floor, there are 2 forces acting on it. There's Fg and Fn. But since those forces cancel out, sigma F is equal to 0. But if you say push the box this way or pull it, whatever, then it will start moving because there is nothing to cancel out your force in this direction. So automatically, the sigma F becomes not 0, specifically sigma Fx. So now I'm going to show you an example of sigma F being 0 and sigma F not being 0. So here we have a little setup. You shouldn't care about the spring, just ignore it, but I'm going to pull it for the funny. And now you might see that this ruler over here, it's bobbing, but net force is somewhat sorta equal to 0 because this mass is holding it down on one end and gravity is on the other. But now let's see what happens when I take off this mass. Ready, set. Oh wow. Okay, so over there, an unbalanced force acted on it now. It was kind of bound to the table by the mass, but when we removed the mass, then it wasn't really bound to the table anymore, and Fg was acting on it at this end. So, if this guy wasn't here to cancel it out, this guy's just going to fall. That ruler stayed at rest, or at least somewhat stayed at rest, until sigma F wasn't equal to 0 anymore, at which it fell. Alright. So now, let's explore how this relates to momentum. So, the thing is, this is inertia. But now, let's talk about inertia in motion. In other words, momentum, or what in Newton's old times they used to refer to as motion. So, momentum is just the short term for inertia at rest, so we'll use it for the inertia in motion, so we'll use it. Okay, what that basically means is that if this has a velocity of, say, x, for example, then it will keep going. It will keep going at the velocity v until an unbalanced force acts on it. So, for example, then you might say, what if you push a block on a table? It slows down and then comes to a stop. Why? Because it's tired? Well, no, because actually, when you push a block, after your hand leaves the surface of the block, there's only really one force that we need to care about acting on the block. And that's the force of friction. Since there's nothing to cancel that out, the force of friction slows this down, making it not constant velocity. But for example, if you had, say, another wooden block and you threw it into space, it would keep going in the same direction in the same constant velocity forever and ever until it either hit something and got sucked in by something. Okay, so that basically means let's examine something here. So now, what is momentum anyway? Well, momentum can be found using the equation mv, and we'll explore this later in the future. And why the m? Well, basically, think of it as like a truck, for example, would be a little harder to stop than like a small little, car. Just a small little car. If they were going at the same velocity, the truck would be harder to stop because it would have the greater mass and this would have less mass. So mass also plays a part in momentum as well. So now, let's explore a scenario where we just have a car riding on the road. Just one lonely car. And so, let's say this car is moving at 5 meters per second and it's 50 kilos. Well, 50 is actually a little low for a car. Not a little, but let's say it's 1,000 kilos. So now, let's say this is at time ta, and at time tb, it's over here. It's still 1,000 kilograms, obviously, and it's still moving at 5 meters per second. Now, notice that it's at constant velocity, which is exactly an example of inertia and motion, or momentum. Now, momentum is constant here, because here it's 5,000 Newton seconds, and here it's also 5,000 Newton seconds, because multiplying the mass by the velocity is the same here and the same here. So momentum is constant when you're at constant velocity. And what is constant velocity? Well, I guess it says it right here. But constant velocity is inertia and motion. And inertia is the center of Newton's first law. Okay, now that we have all that rambling done, let's whoopsie daisies. Let's get the second law started. So let's erase this over here. And just keep in mind that the first law is centered around inertia at rest and inertia in motion. Doink. Okay. So, for our second law, it's probably one of the most famous equations in physics. F net is equal to ma. Now, let's think about this for a second. Stop and think about it. Why? Because notice that P is mv. And then delta P, or change in momentum, is going to be m delta V. You can't really add a delta m because mass is a scalar and it doesn't change and all that kind of crap. And now, well, what we can do is realize this. Acceleration is the change in velocity over time. Please excuse me. And that gives you m delta v over delta t. Do you see what we can do now? Hopefully you can, because that means delta f is equal to delta p over delta t. Mind-blowing. But in fact, sigma f is ma is not even how Newton actually stated it in the first place. Newton originally stated it in Principia like this. Sigma f is equal to delta p over delta t. But this is the modern interpretation of that. So now, this basically shows that force is change in momentum over time. Let me give you one example of this. Let's take two scenarios, actually. So, here we have a car at two different times, and I'm going to draw it simplistically for the sake of time. So here, this is the same car, by the way. So let's say this car has a mass of 1,000 kilograms, and here it has a velocity of 10 meters per second, and here it has a velocity of 15 meters per second. But now, let's say we have this here. The mass is 1,000 kilograms as well. And velocity is 5 meters per second. And velocity is still 5 meters per second a few seconds later. And just to be clear about this, so you can't go saying some funky crap, velocity from time A to time B is always increasing from 10 to 15. And velocity over here will always stay constant. So you can't do any sort of funky crap with me here. So I want to ask you, which one here is an example of Newton's first law and which is an example of Newton's second law? And keep in mind that since this is Newton's second law, this is scenario uno, this is scenario dos. So I want to ask you, which one is an example of Newton's first law and which one is an example of Newton's second law? And before you answer, cameraman, keep in mind that the second law is the change in momentum over time. And also keep in mind that from A to B, velocity is constantly increasing here. And from A to B, this stays the same.
I understand everything. So the first one has to be Newton's first law because it's first one. And second one has to be Newton's second law because it's the second one.
Actually, I'm going to tell you a real sucker. This is the third law of Newton, and this is Newton's fourth law. No, I'm kidding. That would be stupid, just like you, Jimmy O. The real answer is that this is Newton's second law. Why? Well, take a moment to pause and think about the momentum in both of these cases, at both of these times. Momentum over here is mv is 10,000 Newton seconds. But momentum here is mv is 15,000 Newton seconds. There is a change in momentum, and that's exactly what I outlined over there. So this is an example of Newton's second law. While over here, momentum is 5,000 Newton seconds, and also 5,000 Newton seconds over here. So that shows that this is the first law. That this is another form of Newton's second law. So now, this signal is actually taking up a little bit of space, so I'm going to remove it and just write this F net instead. Now we can multiply both sides by delta t. And that gives us F net delta t is equal to delta p. And, well, we can just generalize this to say F delta t is delta p. But you know what else is delta p or F delta t? J, impulse. So, for example, let me give you a J is basically the same thing as change in momentum. So let me give you an example. So, and by the way, let's say that we have two men and they're twins, so they both weigh 60 kilos. They've been eating the exact same food. And now, they are literally the same people, but one wasn't born with the biggest brain. He has the brain the size of a rat, so he naturally jumps and lands on the dirt. And while the second one, he's a little smarter. He sees a random mattress that's totally not suspicious lying a few meters away from where his first brother. So he jumps onto the mattress too, and survives. And they jump with the same initial velocity. They jump with the same vertical velocity. We're not going to talk about horizontal velocity, but obviously you know that the brother who actually had a smart brain had a higher horizontal velocity. But we know that their vertical momentum was the same. So over here, Py initial is 0 for both of the twins. But, so now let's say that this cliff is 45 meters tall. So now, what would be Py final here and Py final over here? Vfy squared is equal to 2Gy, I guess. So Vfy is the square root of 2 times 10 times the height was 45. So their final velocity is the square root of 900, or 30 meters per second, vertically, for both of them. So that means Py final would be 30 times 60 for this guy, and also 30 times 60 for this guy. I guess technically negative, but Vfy is negative 30, so this would actually be negative 1800 Newton seconds on both sides. So why does this one do the thing while this one survives? Well, let's say this one soaks on the mattress for 10 seconds, and this one only has like 0.01 seconds before he just... So, if this guy slows down in 0.01 seconds, then the impulse for them is the same, obviously, because they've changed delta P, but they have the same delta P, but impulse is F delta T, and they have not experienced the same delta T, meaning they won't experience the same force. So the average force is going to be different for the two. So for the guy who, sadly, on the dirt, the average force exerted on him over that one time would have been negative 1800 over delta T would have been 0.01 seconds. So that means he would have experienced 180,000 newtons. And that's exactly why he got sent off to the afterlife. However, the guy who landed for 10 seconds actually had a much less force exerted on him. Only 180 newtons. So you can see that since this one survived because they had a less average force exerted on them over time. This one died because they had a really big force exerted on them over a small time. But you can see their delta P was the same. Anyway, now, instead of talking about J and impulse and getting sidetracked, let's move on to the most hairy one, finding out how law number 3 is the conservation of momentum. So, let's erase this. Okay. Finally, let's get to law number 3. So, law number 3 of Newton says that, ow, if you punch a wall, it punches you back. Let's punch with some rule. Ow. So Newton's third law has many applications all over physics, including punching a wall. But it also has some applications in more formal parts of physics as well. Just give me a second. Sorry. So, law number 3 basically states the force that A exerts on B, or the force that my angry hand exerts on the wall, the same force, but in the opposite direction, will be exerted on the wall, by the wall onto my angry fist. So, let's get... So this is my fist right over here, and once it punches the wall, I know it's not the most realistic of fists, but I'm not Picasso. once it hits the wall, it exerts the force Fa on B, but the wall exerts the same force in the opposite direction of negative FBA. So now, let's apply that to conservation of momentum, but instead of imagining two fists colliding, let's think about two objects colliding. And in fact, I haven't been using this for the entire lecture. I wonder why I'm still holding this red marker. So, well, let's say we have these two balls, and this, do not make a phallic joke, and this is going to be, we're going to assume every single collision made here is elastic. Just keep that in mind. But for perfectly inelastic collisions, momentum is conserved as well, so it works with those two. The only difference between these two is that this one, kinetic energy is conserved, while this one, kinetic energy is not conserved. Alright, sorry, I just had to let that all out. So, let's say that first of all, let's say we have a 1 kilogram ball and a 3 kilogram ball, and I'm not just going to tell you the velocities, just going to say that they're approaching each other, and let's say this is ball number, not number A. Let's label this ball A and this ball B. Do you think B will exert a greater force on A, or A will exert a greater force on B, or they will be the same? So let me give Jimmy over there 4 choices. 1, A is harder on B. 2, B is harder on A. Or let's actually write them using...
I thought you wanted to rewrite the equation.
No, I am giving you an example first. 1, FAB is greater than minus FBA. 2, minus FBA is greater than FAB. 3, FAB is equal to minus FBA. And 4, rubber ducky. Because rubber duckies are cool, but that's not a rubber ducky. Rubber ducky. Okay, Jimmy, choose between these 4 choices. 1, FAB is greater than minus FBA. 2, minus FBA is greater than FAB. 3, FAB is equal to minus FBA. And 4, rubber ducky.
I should have 4, rubber duck. No, that cannot be. I'll go by 3.
FAB is equal to minus FBA.
Right.
But that is actually correct. Good job, Jimmy-O. It only took you 1 attempt. So, FAB is equal to minus FBA. In fact, that was pretty easy because the equation is right up there. So, regardless of what the masses are, they will exert the same force on each other. So, now, let's get started with this. So, let's try and express the change in momentum for B. And I know a lot of you guys like working with numbers, so I'll do that here. So let's label this ball A and this ball B. Let's say this one is 2 kilograms and this one is 3 kilograms. This one is 2 meters per second and this one is 1.5 meters per second. Sure. So now, that's just working with numbers for you guys. So now, how can we express the change in momentum for ball B? Well, we learned the change in momentum is F delta T by just rearranging our previous equation. F net is equal to delta P over delta T. So, knowing this fact, we can solve this problem. Delta P is F delta T, so that means that, let's start with A first. P of delta PA is F delta T, and what does F and delta T represent here? Sorry? F represents the force that they exerted on each other during the collision, and delta T represents the amount of time that the collision took. Because remember, the collision must have taken at least an instant. Couldn't have just happened in 0 seconds. So we have PA final minus PA initial is equal to F delta T. So that means we have MA VA final, or I guess this is more visible to you guys, so I'll use prime in place of final. And we don't need a final and initial for M because it never changes, minus MA VA is equal to F delta T. So now, let's remember this guy and move on to the next. And you can also try expressing this yourself. MAVA prime minus MAVA is equal to F delta T. So you can, in fact, find this change in momentum. Well, actually you can't, but not right now. Let's calm down and just stop doing random things. Now, let's try doing the same thing, but with B. MBVB prime.
Draw a line, or draw a line and then separate it.
Well, actually, the thing.
Oh, do it by it.
Okay.
Do it by it.
Well, actually.
Oh, you did it for A?
Yeah. Wait, I made a mistake. One second. Yeah.
So
Yeah. I know. So actually, the thing is, I made a mistake here. This is before the collision, and after the collision, since this is obviously elastic, they're going to bounce off in different directions. So that means that A will go from having a positive velocity to a negative velocity, which is actually a negative change in momentum. So I'm sorry, I apologize. This should have been minus F delta T. Okay, now let's get PB by drawing a big fat red line. And now you don't need to panic here because B goes from having a negative velocity to a positive velocity. So it has a positive change in momentum. So let's write the same equation for B. PBF minus PBI is equal to F delta T. We don't need a minus because there's a positive change in momentum. So now we have MBVB prime minus MBVB is equal to F delta T. And now we can equate these equations. So since this is F delta T, we can take MAVA prime minus MAVA is equal to, and we just plug in. And remember to keep the minus there because forgetting the minus will muddle all your crap up. So you've got MBVB prime minus MBVB from all the way over there. So now that means we have MAVA prime minus MAVA is equal to MBVB minus MBVB prime. So now, finally, we can add MAVA to both sides and MBVB prime to both sides, giving us MAVA prime is equal plus MBVB prime is equal to MBVB plus MAVA. Now, actually, now that I think about it, I could have done a way simpler version of these, not expanding this into MV and instead just keeping it with a PA. But whatever, we've made our choices. So this is our final equation. But we got to rearrange it first just to make it a little more intuitive. So we've got MAVA plus MBVB is equal to MAVA prime plus MBVB prime. And don't worry that I've switched the left hand and right hand sides. That's like saying 1 plus 1 is equal to 2 and 2 is equal to 1 plus 1. So now that is the equation that we're going to use. Finally. Okay, so now let's try doing this problem, but well, I guess there must have been some purpose for giving you those numbers before. So if this 3 kilogram one leaves with 0.5 meters per second, then what is the velocity of this 2 kilogram one, given that this is before the collision? And obviously the velocity must be negative, as we have just learned. Okay, so pause the video and think about it. Have you paused the video yet? Okay, I'm going to hope you pause the video. So now, the answer is obviously here. So we have MA, VA. So MA is 2 and VA is 2 as well. MB is 3 and VB is 1.5. And MA prime is, sorry, I had to digest that. MA prime, well, wait, why did I put MA prime? I'm dumb. So MA VA prime is 2, and we don't know VA prime. But one thing we do know is that it's going to be negative, so just keep that in mind, just in case. And, I've already made a mistake. I'm so dumb. 3B has a negative velocity, minus 1.5 meters per second. So this should be a negative sign, not a positive sign. So now we've got plus 3 kilograms times 0.5 meters per second. So we have 4 minus 4.5 is 2 VA prime plus 1.5. So minus 0.5 is equal to 2 VA prime plus 1.5, or in other words, minus 2 is equal to 2 VA prime. And how wonderful, VA prime works to be out to be exactly minus 1 meters per second. Jesus. So, as you saw, Newton's third law was just the conservation of momentum in disguise. Well, that's it. Thank you everybody for watching. And don't forget to celebrate Black History Month. Have you clicked out the video yet?